Hi, everybody. This is John Whitaker for the Probability Graduate Level class, and this is our second video lecture. And today, what we want to do is we want to go over some properties of probabilities. We had the definition of probability in our first video lecture. And then we also want to take a look at some examples, and then the second topic of this lecture will be about conditional probability. Okay, let's go ahead and get started with a property of probability. So, as a fact, if A is an event, then the probability of A is equal to 1 minus the probability of A complement, the opposite of A. And so, we're going to do a proof of this, but before I do a proof, let me draw a picture that is a Venn diagram to illustrate this fact. So here is the sample space. This box represents the sample space. And what I'm thinking is the probability of this box is 1, and I'm going to make an analogy that this box is like a piece of land, and the worth of this land is $1. And if we've got some set that's an event, a subset of A, a subset of S, call it A, that's an event, and we want to know what the worth of that piece of property is. Well, here's what we can see. The worth of that piece of property ought to be the worth of the whole box, okay, minus the worth outside of this property that's within the box. And that's exactly what this represents. But here's the proof of it. So, first of all, note that 1 is equal to the probability of the sample space. And then we can rewrite the sample space as A union A complement. Remember, A complements everything that's not in A, that's in our sample space. And these two sets are disjoint. And by one of the conditions of probability, its definition, the probability of a union of disjoint mutually exclusive events is equal to the sum of their probabilities. So what we have is 1 is equal to the probability of A minus the probability of A complement, thus 1 minus the probability of A complement is equal to the probability of A. And that's what we were trying to prove. So that's true. Let's do a quick example. So as an example, let's suppose a die is rolled twice. And the question is, find the probability that at least, let's write it this way. That at least one die roll is even. Okay. I'm going to do this problem in 2 ways. So here's my solution. This is the first way. Okay. The first way is that I'm going to look at the sample. Well, maybe in both ways. I'm going to look at the sample space. So script S. So we're rolling the die twice, and we can get an outcome on the first die roll and then an outcome on the second die roll. So we can get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then we could have gotten a 2, 1. Now 2, 1 and 1, 2 we're going to list as separate outcomes so that we make our sample space consist of equally likely outcomes. So I'm going to consider them different. So I should have a comment here between these. 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. You know it takes a little while to list them all out. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. And then we have 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. Then 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. And finally, the last row, we have 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So that's our sample space, and everything is equally likely. So I'm going to use, in the first way, the classical definition of probability. So the probability that at least one even die roll, that's equal to the number of outcomes that have at least one even die roll over the number in the sample space. And so that's equal to the number in the sample space is 36. So let's just count how many of them have at least one even die roll. In this row, there are 1, 2, 3. In this row, there are 6. That makes 9. There are 3 here, so we're up to 12. And each one of these has an even die roll, at least one. So that's 18. There's 3 here, so 21. I think it's 27 over 36. Of course, that can be reduced. 9 goes in both of them. It's 3 out of 4. That's our answer. 27 over 36. Let's do it another way. So a secondary way of doing the problem is using our property we just had is that the probability of at least one even roll. That's the same thing as 1 minus the probability of the opposite of this, and that is both rolls are odd. Okay. This is equal to 1 minus, and then this is the number of ways that both rolls are odd, over the number in the sample space. So that's 1 minus. Okay. Now, for both rolls to be odd, the number of them, if I look over there, there are 3, 6, 9. So I look at the sample, it's 9 out of 36. So that ends up being 27 out of 36, or the 3 out of 4, which is the same answer. So you have 2 ways of doing it. But one of the things about this property is that it turned out that the counting in the complement was smaller than the counting from the original question. And even though this example is not hard to count in either the probability of at least one even roll in comparison to the probability that both rolls are odd, sometimes you're put in situations where there is a difference of which one's easier to count. There might be lots of outcome possibilities that you don't list and then try to go through. So that's why this property can be beneficial. I just showed you this kind of small example, but I hope that the benefit is clear. Okay. Next thing we want to do is another fact, another property of probability, and that is that the probability of A union B, I'm not saying that, I'll write down a header for this. If A and B are events, then the probability of A union B is equal to the probability of A plus the probability of B minus the probability of their intersection, what they have in common. So if you combine them and take a look, their probability is the probability of each individual one of them added together minus their intersection. We're going to do the proof of it over here, but before I do the proof, let me give that Venn diagram pictorial explanation, and it'll help us in the proof. So maybe here's our sample space, here's the set A, here's the set B. And again, we think of the sample space being worth $1, and then maybe it's a piece of land, and then we are wanting to know the probability of A union B, the worth, if you will, of this region. Combine A with B, just group them together. And so here's what the answer is. The answer is the probability of A union B, the worth of A combined with B, is equal to the probability of A, the worth of A, plus the probability of B, the worth of B. But we counted this region twice. We paid for this twice when we just add the worth of A and the worth of B together, the probability of A and the probability of B. So we have to remove this region, its worth, its probability one time, and that's the probability of A intersect B. And that's why the formula is true. So here is a proof. I would like to start off by noting that the probability of A is equal to the probability of A minus A intersect B. So that is a true statement. Union A intersect B. So that's the way that I'll look at it. So A minus A intersect B is just this part of A. And then we add to that A intersect B, this part of A. And so that's what A is. Now, this is a union. And what we notice is that A minus A intersect B and A intersect B are mutually exclusive events. That is, their intersection is the empty set. So the intersection with this and with this is nothing. So when we take the probability of a union of mutually exclusive events, that's the sum of these probabilities. Similarly, if you work with B, the probability of B could be rewritten as the probability of B minus A intersect B plus the probability of A intersect B. Same argument as what we just had. So, if you take the probability of A plus the probability of B, what that's equal to is the probability of A minus A intersect B plus the probability of A intersect B plus the probability of B minus A intersect B plus the probability of A intersect B. Okay, what I want you to do is just look at these three sets. And we're taking probabilities of them, but just concentrate on those sets. So A minus A intersect B is just this part of A. A intersect B is this part of A. So really, when you have those two parts, they give you A. And then the last one that I want to concentrate on, last set, is B minus A intersect B. That's this part. So when you take this part, union with this part, union with this part, you just get A union B. So this is equal to, because of them being mutually exclusive events, and we're summing up the probabilities, this is the probability of A minus A intersect B union A intersect B union B minus A intersect B, and then plus the probability of A intersect B. But as I said, this set that we're first taking the probability of is nothing more than A union B. So what we get we have the probability of A plus the probability of B, and that's equal to the probability of A union B, and it was plus the probability of A intersect B. And therefore, if we subtract the probability of A intersect B, these are just numbers. So the probability of A plus the probability of B minus the probability of A intersect B. And that's equal to the probability of A union B. And that is the statement that we wanted to prove. So that is the proof. Let's do an example of that. So a die is rolled twice. Okay. And then we're going to let A equal to at least one roll is a 2. B, or set B, or event B, be that both are even. Both rolls are even. And so what we want to find is find the probability of A union B. Okay. So here's our setup. We're rolling the die twice. And A is the event that at least one of the die rolls is a 2, and B is the event that both die rolls are even. So let's look at the sample space kind of again. We had it previously, but I'm just going to write it down real quick. 1, 1, 1, 2, so forth. Then we have 2, 1, 2, 2, so forth. 3, 1, 3, 2, and so forth. 3, 3, and 3, 3, 1. 4, 1, 4, 2, and so forth. 5, 1, 5, 2, and so forth. And then 6, 1, and 6, 2, and so forth. Okay. And so what we want to do in terms of the first way, which is where I'm just going to count, use the classical definition. So probability of at least 1, 2, or, so that's what union means, or this happens, both rolls are even. And that's equal to the number of ways of at least 1, 2, or both even rolls, okay, over the number in the sample space. And that's equal to, so the number of rows that have at least 1, 2, or both being even. In the first row, the number of outcomes for which this happens is just 1. It's 1. In the second row, it happens 6 times. In the third row, it happens, once. So we're up to 8. In the fourth row, it happens, the event where at least 1, 2, or both are even, it happens 3 times. 4, 2, 4, 4, and 4, 6, both rows are even. And so we were at, I think, 8, 11. Then here once, so it's 12. I think it's 15. So the answer here is 15 over 36. And that's our answer. The second way. Put it down here. So the second way is using our formula. So the probability of at least 1, 2, or, so or is for the union, or both are odd, even, That's an A union B. And so the answer is our formula would be the probability of at least 1, 2, plus the probability of both are even, minus the probability of at least 1, 2, and both even, both rows even. And I'm not going to write this out, but I'm going to calculate each one of those three probabilities by using the classical definition because our sample space consists of equally likely outcomes. So at least 1, 2. So at least 1, 2. That happens once here, 6 times here, so that's 7, 8, 9, 10, I think it's 11 out of 36. Plus, both are even. That happens 3, 6, 9 times. Minus the probability that at least 1, 2, and both rows are even. So where does that happen? That happens at least 1, 2, and both rows are even. It happens 3 times here. 2, 2, 2, 4, and 2, 6. So 3. It happens once here in this column, in this row. So there's 3, 4, and then once here, 5. So minus 5 over 36. And that indeed is 20 minus 5. That's 15 over 36. So you see we get the same answer. And in some problems, it'll be easier to use this formula than instead of using the classical definition of probability. But you see an example that it's true, or the fact that yielded the same result in this example. Before we move on, just give me a second to make sure that I got the right answer. I think I did. Yes, I did. Now, next thing we want to do is look at one more probability fact. So the next probability fact is that the probability of the empty set is equal to 0. So here's this proof. Well, note that 1 is equal to the probability of the sample space. So the empty set is the set that contains nothing. So this is the same thing as the probability of the sample space union the empty set. Because if you take everything and throw in nothing, you still get everything. Now these two sets, if you intersect, you get the empty set. So what's in common between everything and nothing is nothing. And so the set that contains nothing. And so since they're mutually exclusive events, by our definition of probability, it's the same thing as probability of S plus the probability of the empty set, which is equal to 1 plus the probability of the empty set, because probability of the probability of the sample space is 1. So what do we have? So we have 1 is equal to 1 plus the probability of the empty set. So the probability of the empty set must be equal to 0. That's a fact. Okay. And you can come across cases where the problem that they're asking you involves taking the probability of the empty set. So I won't do an example of that, but it can happen. I won't do an example of it immediately. A little later on. Next, I want to talk about conditional probabilities. So as a definition, if we're given two sets, A and B, with the probability of A being non-zero, probability of B being greater than 0, then the conditional probability of A given B is denoted by here's the way we symbolize it. Probability of A with a bar B and is given by the probability of A given B is equal to the probability of A intersect B, so what's in common between these two events, over the probability of B. So that's its definition. And we're going to look at examples where we use this. And let's say a card is selected at random from a well-shuffled deck. So I'm thinking about a standard deck of 52 cards, shuffling it, and then we just randomly select a card, and that means that each outcome is equally likely to be obtained for the card. So here's what we're going to find. We're going to have several cards. Find, part A, the probability that the selected card is a heart. B, the probability that the selected card is a heart given that the selected card is red. So the given part is like additional information. So conditional probability has to do with knowing a little bit more information. And here's another conditional probability problem. The first one is probability that the selected card is a heart given selected card is black. Okay, let's do these problems. So the first problem was the probability that the selected card was a heart. That's what probability of a heart. Well, I'm going to think of this as the number of ways of reading a heart over the number of ways of choosing the card. So that ends up being, so the number of hearts in a deck is 32, and the number of cards in a deck is 52. So it's 1 out of 4. So there's a 25% chance you get a heart anytime you just randomly select a card. Part B, and I should back up, Part A is not a conditional probability, but Part B was. So was Part C. Part B was given a heart, and what's the chance of getting a heart given that you have a red card? Okay. So let us use the definition here. So this is the same thing, the definition of conditional probability. Probability of heart and red over the probability of red. And that equals to the number of ways of getting heart and red. So heart and is intersection, heart and red, over the number, over the number in the sample space, over the number of ways of getting red cards, over the number in the sample space. The number of ways of getting a heart and a red card, well, really that's the same ways of just getting a heart. Okay, so that ends up being 13 out of 52, number of ways in the sample space. Over the number of red cards, that's 26 out of 52. And so we get 13 out of 26, which is 1/2. Yeah, that makes sense. That they're telling me to only look at half of the deck, the red cards, because they're telling me that there was a red card chosen. And so it's 13 out of 26, 1/2 for this conditional probability. Okay, the last problem, part of this problem, part C, was to find the probability of a heart given that a black card. So using the definition of conditional probability, this is the probability of getting a heart and black card over the probability of getting a black card. Okay. So let's think, what are our outcomes that satisfy being a heart and a black card? Well, there are no cards that satisfy that. So this is really the probability of the empty set over the probability of the black. That's equal to 0, and the probability of black, well, it's another way of getting a black card over the number in the sample space. So our answer here is 0 out of 26 out of 52, but that ends up being 0. So here, this particular conditional probability is 0. Okay, let us look at another example. The conditional probability. And it says an urn contains 8 white balls and 3 red balls. It says 2 balls are selected. One after another. Randomly. Without replacement. So we've got 8 white and 3 red. Okay, and so what we're trying to find is find the probability that the second ball is white, given that the first ball was red. First chosen ball is red. So in terms of our notation, the way we represent this is the probability that the second is white, given first is red. Okay. And by definition, this is the probability that the first is red and second, I need a little bit. is equal to the probability first is red, and second is white, over the probability that the first is red. Okay? So this is equal to the number of ways that the first is red and second is white over the number in the sample space over the number of ways that the first is red over the number in the sample space. Okay, I've run out of room, but we kind of keep this in mind here. Okay, so what we had written was the number of ways the first is red and the second is white. So we think of this as a sequence of events. And so if you remember the problem, I think we had 8 white and 3 red. So the number of ways that the first one could be white is 3. I'm sorry, red is 3. And the number of ways that the second could be white is 8. Now, the number in the sample space is selecting 2 balls at random. So we got to pick a ball. There were 11 balls in the urn, so there's 11. And then for each one of these possible 11 balls that could be chosen, there are 10 balls to be chosen for the second. All over. All right. Now, the bottom was if the first ball is red. So there are 3 ways that the first ball is red, but now we need to select a second ball. And it doesn't matter what it is. So there's 10 outcomes for each one of the possible red balls that could have been chosen. For the second ball to be chosen, there's 10 ones. And the number in the sample space is 11 times 10. So this ends up being 3 over 8, 11 times 10 times 11 times 10 over 3 times 10. And so that ends up being 8 over 10, which is 4/5. So the probability that the second ball is white given the first is red is 4 out of 5. All right, wonderful. Next thing I want to list is a fact. And it's a way of thinking about conditional probabilities. Here's what it says. It says, if the sample space consists of equally likely events, then the probability of A given B can be computed by reducing the sample space to events where B occurred. And then computing the probability of A from the reduced sample space. We'll do the earning problem again with this type of thought process in just a second. So in other words, what we do is the following. When all outcomes are equally likely, okay, we can put ourselves in the given situation and find the probability of A given B. Okay, so let's look back at that problem. Re-examining the earn problem. So again, it says two balls are selected, random. From an urn containing 8 white balls and 3 red balls without replacement. And we're supposed to find conditional probability the conditional probability of second ball is white given first is red. We did this, and we found the answer to be 4 out of 5. So here's what happens. Remember, I'll draw here. When we start, the urn has 8 whites and 3 red. We choose a red ball. We know we chose red. So what's in the urn now? So this is 8 white and 2 red. So we put ourselves in that situation. And now, what's the chance? The second is white, given first is red. Okay? We're in this position, and so we just count. Okay? How many ways can I get a white ball when I'm in this situation? There's 8 ways. Over how many ways can I get any ball? Well, there's 10. And so this ends up being 4 out of 5. Same answer. One of the things that this illustrates is that often computing conditional probabilities can be an easy thing. Very easy thing. Especially when the question is having to do with what happens next given what happened previously. The reverse type of order of a conditional probability question is a little bit tougher to answer, and we have to use a theorem in general to do that, called Bayes' theorem, that we'll talk about in our 3rd video lecture. But in general, but often, a conditional probability can be easy to calculate if we just put ourselves in the position of the given. Well, as a fact, this stems from the definition of a conditional probability. The probability of A intersect B is equal to the probability of A given B times the probability of B. Again, this is very easy to see. Proof of it, I'll do that very quickly. Well, note the probability of A given B, here I should say well, I'm not going to say it. What I'll do is give a partial proof, so it's a little something like probability of A given B is equal to the probability of A intersect B over the probability of B. So the probability of A intersect B equals to the probability of A given B times the probability of B. Here we're assuming that the probability of B is non-zero. Okay. Let me do one example and then we'll call it quits. As an example, let's say a urn has 8 white balls and 3 red balls. Find, 2 balls are selected at random without replacement. Somebody might say, find the probability that the first ball, let's see if I did the exact same problem, is red, and second ball is white. So that's our question. And so we're being asked, probability first is red and second is white. You can do this problem by listing all the ways that this can happen, just using the using the classical definition. But instead, I'm going to say this is the same thing as the probability that the second is white, given first is red, times the probability the first is red from our fact. Okay, probability the second is white given the first is red. We just did that, and we can calculate it very easily again by just putting ourselves in position that the first was red, so we've got 8 white and 2 red left, and so that means 8 out of 10. Times the probability that the first is red. Well, how does that happen? Well, the number of ways of getting the first to be red are 3, and then the number of ways of getting the second ball is 10. Over here, the number of ways of getting the first ball is 11. Over the number of sample places is 11. For each one of these first balls can be chosen for 10 seconds. So here's what we end up getting. We get 8 times 10 times 3 over 11. Okay. So this is 24 over 110. Insert 4. Produces, of course, but I'll leave the answer there. Okay, ladies and gentlemen, that is enough material for this video lecture. I thank you very much for your time and patience.